Okay, this one is a cone that's got water being poured into it. This time the radius will be changing, right? So you have to picture again the water in the cone. It's taking on the same shape as the cone, and that's going to be key. So you can pause it and read the problem. I've drawn a little picture as well. All right, so identify all the variables in the problem. So there's going to be a volume of the cone they're talking about. There's a height of the water. I should say volume of the water, not the volume of the cone. Volume of that block of or wedge of water, the height of the water, and the radius of the water. So when you picture the water in motion, they're all changing. So none are constant. Okay, so now we want to talk about what the rates are going to be. So all of those variables are going to change to rates with respect to time. So they tell us the rate of change of the height is 1.2 inches per second. They're asking us to find the rate of change of the volume. And remember, that's going to be in inches cubed per second. So what we can't find, you can only have one unknown rate. So what about this dr dt here? The problem is we don't have it and we can't really get it. So what we have to do is we can't have r in our equation when we go to take the derivative. So somehow we've got to get rid of the r. So the key here is to get rid of the r so I don't have the dr dt. And the way I'm going to do that is I need some type of a side equation where I can relate radius to height. So I can make a substitution and write everything in terms of height. So if you think of this block of water up here, I'm just going to draw it more like a triangle, but if you have the shape of the container compared to the shape of the water, they're going to be similar figures because it's filling up the shape. So it's filling up the cone and taking on the shape of the cone of the tank. So they're going to be similar figures. So I can make similar, I can do ratios here. So I have the radius of the tank is 5, and I can compare that to the radius of the top of the water, which is changing at all times. So I'll just call it r. Okay, and if I do the height of the water, it's changing at all times. I can compare that similarly to the height of the tank, which we know is 15. So I can, using these similar figures, I can write a proportion, which is 2 equal ratios. So I'll write it down here. I want to say 5 is to r as 15 is to h. And I want to solve this for r because I don't want r's left in my main equation. So to solve this for r, I'll cross multiply here. I get 15r equals 5h. I'll divide both sides by 15, and I'll get r equals 1/3 h. So I'm now going to have to make this substitution in my main equation. And I got that from these similar figures here. 5 compares with r, 15 compares with h in similar figures. So if I look at my volume formula of a cone, it's the area of the base, pi r squared, times the height of the cone, and then 1/3 because it's a cone. So times 1/3. So there's our volume formula. As you can tell, it's got those 3 variables in it, and we don't want to have radius. Everything's got to be in terms of h. I keep forgetting that I use capital H's here, so these should all be capital H's. So now if I use this and make my substitution, I have volume equals 1/3 pi, and then it's going to be 1/3 h squared times h. Now I don't have an r in this equation, so I can simplify a little bit, and this will be the volume for this particular wedge of water, taking on this shape of a tank that has that same ratio of radius to height. So 1/3 squared is 1/9, h squared times h. So now I've got 1/3 times 1/9. I got my 127 pi, that's pi, h to the third. There's my volume formula. And now it's only got v and h in it, which is good because I want to know dv dt and I know dh dt. So that's what I need, just those two variables. I go ahead and take the derivative with respect to time. The derivative v becomes dv dt. The derivative of this other part, remember this is just a constant, so I do power rule on h to the third. The 3 comes down, and I get 3 times 1/27 is 1/9 pi times capital H squared times dh dt. So now I can plug in what I know and solve for what I need to find. So I'm going to get dv dt is what I'm looking for, 1/9 times pi, times 6 squared times 1.2. Because my height, it said when the height is 6 inches, and since when the radius of the exposed surface area was 2 inches, so it says when the radius is 2 inches, we need the height. So we can use that side equation again. That's how I got the 6. Radius equals 1/3 height. So if I know the radius is 2 inches, I can solve for height. Height is going to be 6. So that's where that 6 comes from. So at that instant, and then they told us the rate of change of the height was 1.2. It was increasing at that rate. So now I can solve for dv dt by simplifying the right side of the equation, and I'll get 4.8 pi cubic inches per second. That means the volume's increasing at that moment. We expect in another second for the volume to increase by 4.8 pi cubic inches.